Hi everyone, my name is Shenling Ye. I'm currently working in the Apple Inc. display division. Today, my presentation topic is automotive heads-up display. Currently, heads-up display is widely used in the aviation navigation and the automotive industry. Heads-up display can provide multiple advantages: the road safety, driving comfort, navigation system information, and the check control message. So basically, the heads-up display contains various functions to improve road safety and driving comfort, which can provide the user data without changing their viewpoint. The key properties of heads-up display include transparency, brightness and contrast, focus, resolution, and color. First, transparency means heads-up display must be transparent for drivers to see through the outside world. And this is very important for a safety issue. The next, brightness is one of the largest issue for heads-up display because a lot of light is lost before it travels into the combiner. Then coating with a narrow band reflector on the combiner can improve the brightness and contrast. The focus issue means collimating the overlaid image at infinity can help to minimize the visual refocusing. Also, in order to improve the image quality, the high-resolution displays should be fit into the heads-up display. And currently, most of the heads-up display use the green wavelength. One of the reasons is in this color, on the wavelength, human visual system has the highest accuracy. And also, in the more advanced heads-up display, full color has been applied in this kind of device. This is the typical optical requirements for heads-up display. You can get here, usually the eye box size is set to 145 millimeter by 80 millimeter. The eye relief distance is around 800 millimeter, and the maximum brightness at the eye box should be larger than 10,000 candela per square meter. And also, the virtual image distance can be achieved in the range from 1.5 meter to 2.5 meter, and the color can vary from monochromatic to the full colors. Here we use the BMW E70 heads-up display as an example to describe the function of the heads-up display. We can see here, basically heads-up display is kind of the projection device, which can include the component one, means light source. Here we use in this E70, it used the LED array to project HUD information. Then component two is the TFT projection display. So it generates the image content and allow the light to pass through like a switch. Then this image light can be bounced back from the plane mirror component 3 to the curved mirror component 4, finally hits to the windshield. The windshield component 5 here act as a deflecting mirror to transfer the image over the road. Then for the viewpoint of the drivers, he or she can see through the windshield to the virtual image as well as the real road condition. Then the projection distance is one of the important features to evaluate the performance of automotive heads-up display. For example, in the E70, the projection image can appear at a distance of 2.2 meter for observer's eye. One of the biggest issue can exist in the heads-up display is this windshield generate incorrect overlaid image. The reason is that due to the glass tilt in the standard windshield to reflect image, you can see here one is from the surface reflection, the red beam, another is inside the windshield glass. The second reflection created the green beam reflected image. These two reflected image will be overlaid by the angle of the taper to in the HUD screen and to the driver's eye, which will result in the incorrect image for drivers. You see this incorrect windshield generated this blurred image. So one of the solutions is to create a taper over the entire area of this windshield, which can prevent the HUD from displaying images twice. The eye box is the space in which the driver can move without his view of the image in the HUD being impaired. So non-movement freedom of eye box is listed as following. You can see from the horizontal direction, driver is number one is the center, and the number two is the left side, and the number three is right side. So usually it can move around 130 millimeter. And for the vertical side, the range is 70 millimeter plus minus 30 millimeter. So also we can see when the HUD image is outside of the white box, the image is not clear. So for this position 2, we can only see the upside of the image. On the contrary, for this position 3, we only can see the bottom side of the image, virtual image. So basically, this eye box defines the field of view for the E70 HUD display. So again, this is optical layout for this HUDs. So here is the traditional image source CRT, and currently we can replace with the micro LED or micro display like a LED array, LED display, OLED, and DMD scanned micro display, as well as other portable multiple designs to fit into the portable HUD application. And this is the we call it the HUD lens. So basically, it's a collimating lens, and to collimating the projection lens to collimating the beam, and also transfer the beam to the combiner. The combiner here is the windshield, and then finally, this virtual image can be shown in the distance away from the driver. The driver can see through this windshield as well as to get this virtual image. So next part is the design part for this HUD display. First, I starting from the HUD lens, we call the projection lens design. So typical specification, I refer to the Professor Larkin's book, Lens Design. So here we can see usually the entrance pupil diameter is around 6 inch, pupil distance to lens is 25 inch, and angular resolution, the requirements is around 1 arc minute in the center, 3 arc minute in the edge. Field of view is 25 degree. Instantaneous field of view is 20 degree, and the maximum distortion must be less than 5%. So now I use the ZMax to do the lens design for this heads-up display. So the starting point is to refer this Larkin's projection lens. So this is a simple HUD lens, and this is original lens file. And here, Larkin's set the display image on the right side, and the eye box is also the left eye, and also the stop sign. Stop is here. In this simple original lens design, only one wavelength choosing, and the field of view is 25 degree, and the instantaneous field of view is 20 degree. The next step, I needed to modify this lens according to the E70 HUD specs. So first, since the imaging micro display is sitting here, so I reverse the image and optical space from the original lens. And the next step is to change the field of view. So previously I already showed the horizontal is around 130 millimeter, and the vertical size is the 70. So for the half, for field of view, you can see I changed X and Y according to the vertical and the horizontal movement. Finally, I changed the stop set to the driver's eye box here. So I get this modified lens based on the E70 requirement. So next one is to design the whole system of this heads-up display. So basically, I already finished the projection lens, we call heads-up lens. The next step is to how to design for the windshield and this folding mirror setup. So here I just simply refer to the one of the example from the ZMax knowledge base. So here I just use the windshield molded as a mirror without consider the taper treatment inside the glass. And this, in order to mimic the real projection lens, I set the eye box stop away from the virtual image around 2 meters. So also this 240 meter mirror and the power mirror, the function is to transfer the projection image finally to the combiner. Combiner is this standard windshield, and the virtual image plane is set to the object plane. And finally, the size of the virtual image is affected by the multiple factors. For example, the distance from the driver to the virtual image plane, the diameter of the eye box, the distance from the driver to windshield, and the size of the opening in the dashboard. So here is the final optical layout. It looks like nice. And here I already did the optimization for the whole system. The target is RMS wavefront minimum. So basically this modified projection lens can be fit into the whole system. And also in this simulation, in this optimization, also I import two constraints. One is the lens thickness and the air gap should be in the reasonable range. For example, air gap definitely cannot less than 10 micron, and the lens thickness also cannot be too thin. At the same time, there's one specific constraint from my previous slides. The maximum distortion also should be less than 5%. So finally, I get this optical layout. And finally, I also did the optical performance evaluation for my designed heads-up display. You can see the MTF is larger than 30% at 2.5 cycle per meter frequency, and the maximum distortion is less than 2%, which is in the spec. Now, also I checked other operation and related parameters. Most of the parameters are in the spec. So, in conclusion, in my presentation, automotive heads-up displays functions have been introduced as well as designed, described. Heads-up displays lens system has been designed and optimized according to the specs of the BMW E70 heads-up display. The system performance has been evaluated and most of them meet the requirements. For the next plan, the tapered windshield design will be considered in the next step plan. Also, images simulation will be tried in the future design. Finally, cost and packaging issue will be taken into account for portable HUD application. Thanks for your attention.